Any questions before I share the screen and we start talking about math?
All of our due dates, class times are still going to be the same from now on as right now? Or we know?
Oh, I don't know. Okay, if I can do it, sure. I think probably Thursday morning is highly unlikely because everything's going to be a mess. I'll probably not have power. Even if you have power, people are going to be busy, checking out damage and trying to clean the brush out of their yards. But we will see. I don't see any problem with having class tomorrow. Thursday and Friday, I don't know. Okay, so we'll just take it one day at a time. All right. Yeah, this is happening way too often now. I never even lost power during Harvey. Of course, I didn't have water for a long period of time, but all right, I'm going to share the screen and we're going to start talking about math. Well, okay, one thing I want to say, this weather prediction, that's math, basically. Math. And the way they, it's very complicated because there are so many variables. But you can model the weather using, okay, in a very simple way, in what's called an idealized model with 3 little differential equations. And even that, the behavior of the solutions of those is very complicated. But the way people model the weather now is that, well, various groups have their great big gigantic models and they decide what's important to put in it and what's not, what kind of effects to put in. And then they take their model and they put in all the data. Getting enough data is another problem. Without data, it's hard to run the model. But they get the data, they run their model on supercomputers, and they make a prediction. Okay, and there are like 16 of these great big models out there. If the models agree about the prediction, then there's pretty high certainty of what's going to happen. If they don't agree, then there's a whole lot less certainty. But that's basically the way they do it. Modeling the weather is a very difficult problem because of all the different variables, because of something that happens over here that affects something that happens over here. That's called sensitive dependence on initial conditions. And what's very interesting, I think. Okay, but let's talk about calculus, because before you can understand any of that, you need to understand calculus. I'm going to share the screen. Oh, that's my other class. Okay. I like the way that Notes translates my titles. Precise, differ, limit. Okay. But that does at least help you to keep it straight. All the notes, every day after class, I turn this file that we're making on Notes into a PDF file, and then I send it to myself, and then I can upload it into Blackboard, so it's all there. Okay, so before we talk about we sort of had a baby definition of a limit last week. I'm going to at least tell you the precise definition, one that you would need to use if you really wanted to prove things. We're not going to do a whole lot with it. I guess the idea is more important at this point than really getting into the details of the rigor. But before we get into that, let's do some more limit problems. So this one, show that the limit as x approaches 0 of the absolute value of x is equal to 0. Let's graph the absolute value of x, that function. So we have f of x equal to the absolute value of x. Remember, the absolute value of x is defined to be x if x is greater than or equal to 0, and it's minus x if x is less than 0. So the graph is really a two-piece definition. And maybe I'll make that in a color. Graph, it's x if x is greater than or equal to 0. So the diagonal line there. And it's minus x if x is less than 0. Okay, because if you have a negative number, such as minus 1, so the absolute value of minus 1 is minus 1, which is plus 1. Okay, and that side looks like that. Okay, so that's the graph of the absolute value of x. And then to evaluate the limit, I never leave enough room. Okay, what we're going to do, since this is defined in two pieces, I'm going to evaluate the limit from the left and the limit from the right. Let me go back to a black pencil. Okay, so the limit as x approaches 0 from the right of the absolute value of x, that's coming in this way. That's the limit as x approaches 0 from the right. Well, these are positive x's. If you're approaching 0 from the right, remember x is not equal to 0 itself when you're looking at limits. So x would be a positive number, so the absolute value of x is just x. Well, if x is going to 0, the limit is 0. The limit from the left well, the absolute value of x is equal to minus x when you're coming in from the left because you're looking at negative numbers, okay? But if x is very close to 0, so is minus x, it's just on the other side. That's equal to 0. So we have that the limit as x comes into 0 from the right is equal to the limit as x comes into 0 from the left. And that means the limit exists. Right? We said that if you have a limit L, then the limit from the, plain old limit L. The limit from the left is L, the limit from the right is L. If the limit from the right and left are different, then you have no limit, but they're the same here. Any questions about that? Okay, so let's look at this next example. Let me maybe make a line between these. If I change this a little bit, okay, and look at the function absolute value of x over x and look at the limit as x approaches 0 of that, well, let's graph that function too. Graphing helps a lot. Let's see, so the absolute value of x over x is equal to x over x if x is greater than 0. Zero is not in the domain of this function. So I can't talk about x equal to 0. Get 0 over 0, which is not a number. And absolute value of x is minus x, if x is less than 0. So the second part would be minus x over x. And that is then x over x is 1. And minus x over x is minus 1. So this graph (1 minus 1), I'll do it in red. It's going to be basically two horizontal lines. And there's, okay, no value at 0. So I put a little hole there. Okay, well, looking at that picture, pretty obvious that there's no limit. And the reason is, okay, what we said before, that the only way you can have a limit is if the limit from the left and the limit from the right exist and are the same. Okay, so the limit, whoops, okay. The limit as x goes to 0 from the right of the absolute value of x over x, well, that's the limit as x goes to 0 from the right of 1, right? We just worked that out. And that's a constant, so the limit is 1. The limit from the left is minus 1. And they are different. The limit from the left is not equal to the limit from the right. So no limit. Okay. Any questions? Okay, I don't hear anything, so I assume no. Let's look at one or more of these defined in two pieces things. So here f of x is the square root of x minus 3 if x is greater than 3, and it's 6 minus 2x if x is less than 3. Does not say what happens if x is equal to 3. Okay, so 3 is not in the domain of this function. So what is, let's look at whether we can find the limit as x approaches 3 of this function. Okay, well, I'm going to sketch this graph in a minute, but I'm going to look at the limit from the left and the limit from the right and see if they are the same number. Okay, so the limit as x approaches 3 from the right of the square root of f of x. That's from the right. That means I'm using that piece. Okay, that's the limit. Okay, two people came into the waiting room. Scott, let me go back and let them in. Okay, there. Okay, well, they left. Sorry, it's kind of a pain when people come in at 17 after and okay. So that was for nothing. Okay. The limit as x comes into 3 from the right of f of x is the limit as x comes into 3 from the right of the square root of x minus 3. Okay, and that's a power function, basically, a composite with x minus 3. 3 is in the domain of this function, and we can use the direct substitution property, or actually it's continuity from the right. Okay, for this piece, but that's just going to be the square root of 3 minus 3, which is 0. Okay, and then coming in from the left, now we're using this piece. Okay, of 6 minus 2x. And again, well, this is a polynomial. We can just use the direct substitution property. And that's 6 minus 2 times 3, which is also 0. Okay, so the limit from the left and the limit from the right are the same. And that means, well, no, okay. That, and now, there we go. That means that the limit, plain old limit, exists. So the limit does exist for this function. And let's graph it. Okay. And let's see if I can do this without getting into too much detail here. The square root of x minus 3, that's just the square root of x moved over to have it 0 at 3. Okay, so that's what 3 is where the change occurs. 3 is not even in the domain, so I'm going to put a little hole there. But the square root of x minus 3 looks like this, something like that, rough sketch. And then this piece is a line coming down to 0. So I'll call it, let's say 6 minus 2x, so it'll go through that point. And so it comes in like that. So even though this is defined in 2 pieces, and it's not defined at 3 itself, it's got a limit there. Any questions? Okay. Okay. Now we come to the precise definition of limit. I remember when I took calculus in 1965. Okay, long time ago, dark ages. Okay, so I spent hours in the library trying to make sense of this definition. And it didn't really stick until I took something called analysis, which is really understanding the underpinnings of calculus, okay? Understanding in real depth and proving everything very carefully. And then it clicked. But, okay, here it is. Suppose f is a function defined on some open interval that contains a, except possibly at a itself. Okay, so f does not have to be defined at a, but it has to be defined when x is close to a. Then we say that the limit of f of x as x approaches a is L. So I'm defining this. And we write, okay, this notation that we've already talked about, which is, you say the same way as we just said that. Okay, so that's notation there. Okay. Okay, here's the definition. If for every number epsilon greater than 0, there is a number delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus a is less than delta. Okay, so what is that saying? Well, it says that if I want to make f of x close to L, okay, so that's what this is really talking about, getting f of x close to L. What I have to do is to make x sufficiently close to a, and that's what that little piece is talking about. And notice it says that the absolute value of x minus a is greater than 0. Again, when we're talking about a limit, we don't want x to be equal to a. Delta, the number delta, depends on the number epsilon. So epsilon's got to be an arbitrary positive number. And then given that positive number, you can find this delta. Okay, but the smaller you make epsilon, probably the smaller you got to make delta. But it's saying that we can make f of x sufficiently close to L. No, wait a minute. Nope, scratch that. We can make f of x arbitrarily close to L by taking x sufficiently close to a. It's the same definition as we had before. But this one you can use to actually prove things, which we're not going to do much of. Yeah, absorbing this and really learning how to use it takes some doing. Okay, but you can also define left-hand limits and right-hand limits. So a right-hand limit, we say that the limit as x approaches a from the right of f of x is equal to L if for every number epsilon greater than 0, there is a number delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever a is less than x is less than a plus delta. So you're only, oops, did I get the wrong? Yeah, no, I got the right side. That's good. Okay. That's from the right. And of course, coming in from the left, it's similar. And let's just see if I can just change it on here. And I'll put this in red. So left-hand limit. And this would be now the limit as x approaches a from the left. If for every number epsilon greater than 0, there is a number delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever a minus delta is less than a, x is less than a. Okay, so the red defines the left-hand limit. Okay, so we've got limits defined carefully now. And we talked a bit about continuity. Saying that a function is continuous at a number a means the same thing as that f has the direct substitution property at a. Okay, same thing. And here it is written again. F is continuous at a number a if the limit as x approaches a of f of x is f of a. Okay, And this really is saying three things. It's saying one, that f of a exists, that is, a is in the domain of f. It says two, that the limit as x approaches a exists. And three, that 1 and 2 are equal. Okay, that the limit as x approaches a of f of x is f of a. And we noted yesterday that, okay, direct substitution property, equal continuity, holds for polynomials, rational functions, the trig functions, logs and exponentials, the inverse trig functions, didn't mention those yesterday, as long as you take a number that's in the domain of those functions. And also product, sums, differences, quotients, same holds for those composites, okay? You have combinations of functions. As long as a is in the domain of whatever resulting function you have, you've got continuity for that function. Are there any questions? Is anybody there?
We're there. I'm just listening.
Yeah.
Okay, good.
Yeah.
It's a lot. It's a lot of like math theory, I guess. I'm listening, trying to get it.
But in mathematics, okay, and we're not doing it so much here right now because you all are beginners, actually, okay? So I don't want to throw too much at you at once. But in mathematics, you must say things very precisely. You must say exactly what you mean. And that means you don't mean anything more, you don't mean anything less, you mean exactly what you say. And learning how to do that, it takes some time and effort. Okay, but let's look at some functions and figure out where they are discontinuous. And okay, if a function is not continuous at a number a, it is discontinuous at that number. Okay, so f of x is x squared minus x minus 2 over x minus 2. We'll graph that in a minute, but I don't really have to graph it to tell that that function's not continuous. Where is it not continuous? Obviously. Okay.
Two.
Two. Yes, thank you. Because if you try to put 2 into that function, you're going to get a 0 in the denominator. Okay. You cannot divide by 0. So 2 is not in the domain of f. So f is not continuous there. F is continuous everywhere else. So given a number that's not equal to 2, f is continuous there. This is a rational function, the quotient of two polynomials. That's supposed to be an I. Okay. So f is not, this function is not continuous at 2. Can't possibly be. 2 is not even in the domain. What about this one? This is defined in pieces. Only one piece is very small. Okay, so let's graph it. 1 over x squared. Oops, how did I get to yellow? Okay, well, don't need the negative numbers. This function is positive for every value of x. This function is defined at each real number. And okay, f of 0 is 1, but that point right there. But what happens with that 1 over x squared? My phone's ringing, I'm sorry. And it's nobody. I should just unplug it. Just a minute, I'll do that. Well, I can't cover my windows with plywood. I have 22 windows in a small little house, and it's just no way. Okay, back to the math. If we put in 1 for x, 1 over x squared is 1. If we put in, okay, I want to get close to 0, right? Because 0 is where the change is here. It's the interesting number. If I put in 1/2, say, that's a little bit closer to 0, I get 1 over 1/2 squared. 1/2 squared is 1/4. 1 over 1/4 is 4. If I put in 0.1, I get 1 over 0.1. So 1 over 1 over 10 is 10. And okay, these numbers are getting big pretty fast. 1 over 0.01 is 100 and so forth. These numbers are getting very large. So coming in from the right, okay, I've got a vertical asymptote at 0, and that's the function looks like this. Okay. Coming in from the left, not enough room, of course. Coming in from the left, same thing happens. In fact, okay, if I put in plus or minus 1, I get the same thing. So it's symmetric about the x-axis. Plus or minus, plus or minus. So I get, let's see if I can draw it. Same, yeah, these are supposed to be mirror images of each other, but that's the basic idea. So you have a vertical asymptote at 0. Okay. And that means, well, you can say, well, there is no limit. There is no limit. When you got a vertical asymptote, there is no limit. So the limit as x approaches 0 from the right of this function is plus infinity. And plus infinity is not a number. So that means no limit. And coming in from the left, likewise, it's plus infinity. So no limit. And I gotta learn to leave enough space. Okay. No limit at 0. All right. So what this says is that overall, the limit as x approaches 0 of f of x, well, it's plus infinity, which is not a number, so there's no limit. Saying plus infinity means you're saying something about how the lack of a limit occurs. What this is saying, the limit as x approaches 0 of f of x is plus infinity, is that the closer and closer and closer I get to 0, the bigger and bigger and bigger the values of f of x are. So f of x, you say, is increasing without bound, and that's one way to fail to have a limit. Okay, maybe I'll make that a little more precise tomorrow, this kind of limit being plus or minus infinity. But overall, so there is no limit at 0. So it is discontinuous there. Okay. So that's another way, even though this function is defined at 0, but that doesn't change the fact that there's no way to make that into an unbroken curve by filling in a point or something. Okay, what about this function? And actually, part C, that's almost the same as part A, except now we have defined what happens at 2. Remember part A, we looked at this function, okay, x squared minus x minus 2 over x minus 2. 2 is not in the domain of that function. Now we put it in the domain by changing the function a little bit. Okay, so now f of x is x squared minus x minus 2 over x minus 2 if x is not equal to 2. If x is equal to 2, we get 1. Well, let's look at the limit from the left. Well, just look at the regular limit. I think that's sufficient. Okay, so let's look at the limit as x approaches 1. 1's the interesting number, I guess. This function is continuous at every other number, because at a number that's not equal to 2, you've got this rational function on which that function is okay, tongue is twisted. If a x is a number that's not equal to 2, this function is continuous at that x, because x squared minus x minus 2 over x minus 2 is a rational function that is defined at that number. So you've got the direct substitution property, you've got continuity. But if x is equal to 2, and so I wrote wrong thing there, if x is equal to 2, then there is a question. Okay, so if x is, if I'm looking at the limit as x approaches 2 of f of x, well, remember, I don't really want to use this at all. Okay, I want to take x's that are close to 2 but not equal to it. So that means I'm using this piece. And
essentially, you're going to try and find out if the closest you can get to 1 is to 2 is equal to 1.
yeah, it's okay. I think you kind of see what's coming. Okay, I'm going to do what we did yesterday, which is do the little algebra on this rational function, right? Does everybody see why I can replace f of x with that rational function right now? It goes back to when you're talking about a limit, you want to know what happens to f of x when x is close to 2, but not equal to it. Okay, so as far as the limit goes, x is not equal to 2. If x is not equal to 2, that means f of x is that has that rational function value. Okay, so let's do some algebra. Oops. That's the limit as x approaches 2. Okay, that, oops, how did I do that? Okay, limit, there. Okay, well, the bottom doesn't factor, but I think the top does. And let's check that. Okay, so minus 2x plus x is minus x here. That works fine. Okay, so the x squared minus x minus 2 factors into x minus 2 times x plus 1. Now I've got x minus 2 as a factor in both the numerator and the denominator, and I can cancel out the x minus 2's. Okay, well, the limit as x approaches 2 of x plus 1, now that's just a polynomial, and I can just plug in, use the direct substitution property or the continuity. That's 3. Okay, well, is this function continuous at 2 then?
Yes.
Well, thank you for answering, but no.
But no.
Yeah, it's not. Okay, why not? Well, it's got a limit. Okay, so the limit exists. And it's equal to 3. F of 2 exists. And is equal to 1. But 3 is not equal to 1.
Oh, okay. I get it.
Okay, so in fact, and of course, now, need to leave a lot more space. Let me graph that function. Okay, part C. Okay, so I'm going to graph f of x equal to and what we just noted that as long as x is not equal to 2, that rational function x squared minus x minus 2 over x minus 2 is equal to x plus 1. Okay, so try that again, make it straight. Well, that's not much better. Okay, but whatever. Let's see, and I care about getting close to 2 here. Okay, so x plus 1, it's got a little hole right there. That's on it, so but this is actually the graph of the function in part A, because that function, well, was that, and it was not defined at 2. So there's a little hole there at 2. But, okay, the function in part C was this one, which has changed a little bit. And function in part C has that point on it, all right? So you got a little hole in the line. That point looks like just dropped down or something. That is not continuous at 2 because of the fact that the limit as x approaches 2 of the function is not equal to f of 2. Okay, so yeah, so there are really 3 things. If the function fails to be defined at a number, it's not continuous at that number. If the limit as x approaches a of that function does not exist, or no, yeah, does not exist, it's not continuous at that number. But if the function is defined at a and the limit exists at a, they have to be the same thing for it to be continuous. The limit as x approaches a of f must be equal to f of a. So let's see. So none of these functions were continuous. Oh yeah, but the problem was to find where they were discontinuous. Okay. Yeah. So not continuous at 2. Any questions? How are we doing on time? Oh, only 5 minutes left. Okay. Okay, well, you can also talk about continuity from the right and continuity from the left. Okay, so you say that f is continuous from the right at a number a. Okay, so right here. If the limit as x approaches a from the right of f of x is f of a. And okay, I can also no. I can also talk about the limit from the left, continuity from the left. So limit as x approaches a from the left of f of x is f of a. And so the red is from the left and the black is from the right. You say that if it's continuous on an interval, if it's continuous at each number in the interval, and if the interval has a left endpoint, if the interval contains its left endpoint, well, some intervals don't have a left endpoint. Oh dear. Looking at the model of the hurricane on the TV, it's not looking good. Okay. Yeah, if your interval's got a left endpoint that's contained in it, then f is continuous at that left endpoint if it's continuous from the right. And same thing if it's got a right endpoint and it contains that right endpoint, it's continuous at the right endpoint if it's continuous from the left. And let's look at an example of that. Oh, it's 8:52. Maybe I will leave this. We'll pick up here tomorrow, okay? Let me go back to the unshared screen. Okay, does anybody have any questions? Okay, if not, the next few days, well, I think Wednesday, tomorrow should be no problem as far as having class. Thursday and Friday, well, we'll see. I'm highly doubtful that we'll have class Thursday unless this forecast, yeah, unless it changes and this thing really misses us. Probably we're going to have very bad problems Thursday morning. So we will see if I'll try to let you know if I've got power. Okay. If I don't have power, I don't have internet, I really can't contact you.
I have a question.
I might be able to do it by phone, but I don't know. Yes, ma'am.
Okay, so you probably will have, but maybe some of us won't. So what would happen in that case?
Right. Well, the notes will be posted, Daniel. So no problem there. I'll be posting the notes every day. There will also be recordings available. Okay. Mr. Flores is putting them on YouTube. I'm also recording them here, and I will put a link to the recording on Blackboard. So you'll have those available. Yeah, you'll have class available whether you were here or not. Okay, well, hope things turn out better than they're looking like they're going to turn out this week, but not much I can do about it. So anyway, goodbye, y'all.
Bye, and try to stay
Goodbye.
safe.
You do too.
Even
All
on
of
this.
you. Okay. Yeah. Okay. So I'm going to end the meeting.